All right, welcome. Review session number 2. If you haven't picked up your retest, if you took the retest, they are down here. Section 2's over here and Section 3's over there. So you're welcome to come down and pick them up now if you'd like. All right. In Friday's session, we did get through the first 2 chapters, thermodynamics and kinetics. Okay. So we're just going to keep on going. That video from Friday night is posted in Blackboard. So if you missed the Friday session, you can hear all the wonderful things we talked about, I guess. All right. So chapter 15 is the general equilibrium chapter. This is a chapter before we got to acid-base equilibrium. So this kind of just set up what equilibrium is, how you do the equilibrium expression, how do you do an ice table, what is Le Chatelier's principles, what is the reaction quotient, all that good stuff. You saw that stuff repeatedly in the other chapters, but this is where you first saw that. And this is already doing that. That's great. All right. So the first thing, know what we mean by equilibrium. Okay, so this study guide is also posted in Blackboard. So what are the 2 definitions for equilibrium? How about 1? The rate of the forward reaction equals the rate of the reverse reaction. That's exactly right. Sorry about that. Okay. So we typically think of reactions as starting with reactant. It doesn't have to be that way. But as the reaction started, reactant would go to product. After a certain amount of product builds up, products will come together and reform reactant. Okay. And at some point, the rate of reactants going to products will equal products coming back to reactants, and we have reached equilibrium. What is a second definition? Has to do with concentrations. And then there was silence. Okay, so the concentrations, reactants, and products are no longer changing over time. Okay? And that's a consequence of rate forward equaling rate reverse. Okay? If reactants are going to products at the same rate that products are coming back to reactants, those concentrations will no longer be changing. Now, it doesn't mean the reaction has stopped. Okay? It's a dynamic equilibrium. There's continuous reaction going on. It's just that the 2 directions are going at the same rate. All right, so those are the 2 definitions of equilibrium. I think you can all write an equilibrium constant expression by now. Is that true? Okay. Make sure you know that we can, in this chapter we talked about both writing, if we had something like, and I keep going back to this reaction, but it has good coefficients. We could write a Kc expression. And what does that C stand for? Concentration and molarity. So we can write our equilibrium constant expression in terms of molarity, but it is products raise the power of the coefficients, divided by reactants, raise the power of the coefficients. So you've seen this many times, but you wouldn't want to miss a problem on the final that just says, what is the correct equilibrium expression for this reaction? Okay? But we can write it in terms of molarity. We can also write it in terms of pressure. So it would be the same form, pressure of ammonia squared over pressure of hydrogen cubed times the pressure of nitrogen. And what unit of pressure is used? Yeah, atmospheres. Okay, ATM. Okay. So Kc is molarity, Kp is pressure. Yes.
Only when it's like involved gases, right? Like solids and liquids.
Yeah, so the next statement, which is kind of scrolled off the bottom of the screen, says make sure that you know that pure solids and pure liquids do not enter into the expression. Okay? But gases and then also aqueous components. Okay? So like when we got to, we didn't have aqueous things in this chapter, but when we got to acids and bases, those are all aqueous solutions. Solubility reactions are all aqueous solutions. Can I get in your way, Logan? All right, sorry. All right. Okay, so there's the next bullet point. We do not include pure solids and pure liquids in the expression because as long as there's some solid present, okay, and it doesn't all react or whatnot, that there's solid there in equilibrium and liquid as well, the concentration is not changing, and that just it gets incorporated as another constant, okay, into the equation. All right. Big part of this chapter was learning how to solve for x in an ice table. And you got a lot of practice over the course of this chapter, the acid-base chapter, even the buffer chapter, solubility, things like that. Okay? Do we want to work a problem? Yes. Okay. Let me find one. All right, here we go. Okay, if I can spell constant, that would be nice. All right. Give me a second to get all of that down. Oh, sorry. Got a memory issues going on here. Guess we could try going to simple color scheme. I'm not sure what colors I would get. Okay. All right, so we have the reaction. So where do we start? Writing what? Okay, so we could certainly start writing our Kc expression. Let's write that on the side here. Kc, which is 54.3, concentration of Hi squared over H2 times I2. We will certainly need that. All right, what else do we need to do?
Write down the initial concentration.
Okay, write down the initial concentration. So we do need to set up our ice table. We have 0.5 moles of hydrogen and iodine in a 2-liter container. Okay. So we do need this in molarity. So moles divided by liters. Find 0.25 molar for both hydrogen and iodine. What about hydrogen iodide, the product? 0. Okay, so it's just saying we're starting with reactant. Is this system at equilibrium? Why not? Why is this system not at equilibrium? Well, yeah, so you could look at it as too much reactant. I would look at it as we don't have any product. Okay, so at equilibrium, we're going to have reactant and product present. Now, the equilibrium might lie to one side or the other, but we're going to have both present. So if you see a 0, right away, you can say, oh, well, we're not at equilibrium. Okay, now this one, you can look at your K, 54.3. We should actually end up with a little bit more product than reactant. Okay, but seeing that 0 for product right away, you should say, oh, not at equilibrium. So we definitely will shift to reach equilibrium. It has to go to product in this case. We have to make product. So our reactant will decrease. And then how much product will we get? 2x. So don't forget that coefficient of 2. And at equilibrium, 0.25 minus x for both the reactants, and 2x for your product. Any questions on setting up the ice table? You'll probably have to do a few of these on the final. Okay? All right, what do we do with those equilibrium amounts in terms of x? Plug them in. So we have our expression here. Plug those in. Don't forget that you see the coefficients twice. So we have a coefficient of 2 for hydrogen iodide. We see it in the 2x term. And we also have a squared term in our equilibrium expression. Okay, so we see that 2 here and there. So it's 0.25 minus x times 0.25 minus x, which is 0.25 minus x quantity squared. All right, so can we make the small x approximation for this one? I hear yes, I hear no. Just try it and see what happens. When can we make the small x approximation? Yeah, when your equilibrium constant is pretty small, typically 10 to the minus fourth or smaller. Okay, it tends to have to be pretty small. There are other factors that come into play. Concentration will come into play as well. But this certainly is not a small k. So we cannot make a small x approximation here. But I chose a pretty easy problem here because we do not need to solve a quadratic unless you really want to. Anybody want to? No. Okay. So what do we do with this to simplify this one? Square root. So we have a squared term here in the numerator, a squared term in the denominator. We can take the square root of both sides of this equation. And when we do that, so let's see, square root of 54.3 should be a little over 7. 7.369. And then the square root of 2x squared is just going to be 2x. And the square root of 0.25 minus x squared will just be 0.25 minus x. Everybody okay with that? All right, now we do have to do a little algebra. We need to multiply both sides of the equation by 0.25 minus x. So we're going to end up taking 7.369 times 0.25. We're also going to take 7.369 times a negative x. We'll get 1.842 minus 7.369x is equal to 2x. Let's go ahead and add 7.369x to both sides. So that will be 9.369x is 1.842. Almost there. Divide by 9.369. 1.197. Yeah, so to 3 sig figs, which is I think what we have, x comes out to be 0.197. Unit would be what? Molarity. Since we were using Kc and these were molarities given in the problem, our x is molarity. Are we done? We're pretty close though, right? So we have x. The problem said solve for the equilibrium concentrations of all things in that reaction. Okay? So the concentration of HI is 2x, so 2 times 0.197. And it actually came out to 0.1966, so when I multiplied that by 2, I ended up with 0.393. Okay, so if we just took this 3 sig figs here, we'd get 0.394. I had another digit in my calculator, so when I doubled it, I got 0.393. Okay, and then the other two, hydrogen and iodine, are equal at 0.25 minus x. .053. Look okay? What should you do now if you have time?
Do the 5%.
Yeah, plug it back in and solve for K. Okay, and it really doesn't take too long because you have the two concentrations. So we just have to go HI squared. So look up at the top left here. Kc is HI squared over H2 times I2. Now we have rounded these a little bit, so it might not come out exactly right, but if we double check this, we're just going to take HI squared, which would be 0.393 squared, H2 times I2, so we could have squared that as well. And I come up with 55.0 to 3 sig figs. So did we do it right?
Relatively, yeah.
Yeah, it's probably just rounding. If we carried extra sig figs here in these two numbers and here, but we're pretty close to the 54.3. So we probably solved this correctly. Okay. Do the concentrations look like what you'd expect for an equilibrium constant that's about 55, 54.3? Should we end up with more product? Yeah. So we did end up with more product than reactant. All right, so there's our ice table. So watch for the possibility you could have a problem where you have a squared term in the numerator and denominator, square root. You certainly will see small x approximation on the exam. We'll probably save that calculation until we do a weak acid or weak base calculation tonight. But you certainly need to be familiar with that. Quadratic equation, you might have to set one up. You might have a problem that says, set up your ice table, get it in the form of a quadratic equation. What does the quadratic equation look like? Okay, but that you don't actually solve it. So a quadratic equation in the form ax squared plus bx plus c equal to 0. So you might see that. All right, we'll come back to the small x approximation. You should be familiar with that. And we'll check the 5% rule at that time as well. Those kind of go together. Okay, but let's save that for a weak acid or weak base calculation. We kind of just talked about what the magnitude of K tells you, but let's just reinforce that. And that doesn't look like a greater than sign. So if we have a K much greater than 1, so that means we have a very large K. What does that tell us at equilibrium? Products are favored. So we're going to end up with mostly product at equilibrium. Okay, so the magnitude of your equilibrium constant is really important. And it's always a quick way that you can check to see if you're kind of in the right ballpark with your answer. And then the other direction, if K is very small, much less than 1, what do we have most at equilibrium? Reactants. So reactant favored, mostly reactant at equilibrium. Okay, so make sure the magnitude of K tells you quite a bit, actually. All right, next thing, reaction quotient. You saw this a few times throughout these equilibrium chapters. All right, so calculating Q is actually fairly easy. It's set up the same way as K. Okay, so it's products over reactants raised to the power of the coefficients. But what does that little superscript 0 mean? Subscript, sorry. Means the initial. So typically when you're going to calculate Q, you're given initial concentrations. You calculate Q just like you would calculate K, but those initial concentrations probably are not equilibrium. And so we're going to get a value for Q. Okay, so calculating it is pretty straightforward. Just calculate it like K, but with the initial amounts, you start the reaction. And then what do we do with that value? Compare it to K, exactly right. Okay, so Q by itself doesn't tell you anything. Okay, so you can't just look at the number that you get for Q and say, oh, well, it's a large Q, so it must go to products. Or it's a small Q, so it must go to reactants. You have to compare it to the equilibrium constant. And really the two possibilities are, you will find that Q is greater than K, or Q is less than K. The third possibility is Q is equal to K, but it's unlikely that you would start the reaction at equilibrium. Okay? All right, so if Q is greater than K, which way does the system shift to reach equilibrium? Okay, it shifts left. So you can memorize this. I like to think of this as, I guess it might help if I had a laser pointer. Looking at my expression here, if Q is too large, then I have too much product. My numerator is too big. So I need to get rid of product. Okay, so it's going to go from product to reactant. So product will get smaller, reactant will get larger, and eventually we will get to the equilibrium constant. Because remember, we eventually want to get to Q equal to K. So Q is too large, products go to reactants, the numerator gets smaller, the denominator gets bigger, we get a smaller Q value. The other direction, Q less than K, Q is too small. How do we make Q larger?
Shift right.
Shift right, we make more product. Okay, so if we make more product, our value will get larger. Okay. Now, just remember, some of the equilibrium, you'll know what direction it's going to go. The ones that we're going to know right away is if there's a 0 on either side, just like the previous problem we worked. Okay? When there was a 0 in our ice table, we know it had to go and produce some of that product. Okay? So look back at the ice table, which is now scrolled off the screen. Where you're going to have to calculate Q is if you have the amounts of all things in that reaction. Okay, so you're given reactants and products, and you don't know which way it's going to shift. Okay. All right. Le Chatelier. The French guy. So let's look at this reaction and just do a couple of different scenarios with Le Chatelier. Let's do Oops, sorry. Sometimes the pen gets stuck. All right. Wow, we've been going for 31 minutes already. That's exciting. All right, I think that's most of the possibilities that I can think of. So again, Le Chatelier's principle, your system is at equilibrium. Okay, so you're starting at the equilibrium position, and then you make some change to that system. Now that change may or may not impact that equilibrium. I think about 4 of these will and 2 will not. But if we make a change to the system in equilibrium, it might impact that equilibrium, and the system is going to shift one way or the other to reestablish equilibrium. Okay? So the first one, we're going to add some N2. We're going to add some of that reactant. Which way will it shift to? So by adding N2, it will no longer be at equilibrium. It's going to shift one way to reestablish. Which way?
Right.
It's going to shift right. Okay? So Le Chatelier says if a stress is applied to a system at equilibrium, it's going to shift to partially offset the stress. So the stress in this case is changing the concentration of our reactant. It's going to shift to remove some of that reactant. So it's going to shift to product, shift right. All right, now let's remove some hydrogen gas. Which way will this shift? It'll shift left. So we're going to pull some hydrogen gas out of the reaction vessel, and it's going to shift to replace some of what we remove. So this one will shift left. All right, decreasing the volume of the container. What is the stress that is applied to that system? What is it? It's pressure. So if we squeeze on that gas, if we push it into a smaller volume, our change is an increase in pressure. Okay, so that is the stress on the system. So the system is going to want to shift to decrease the pressure. Okay, so we're going to offset this change. So the change was cranking the pressure up. The system will shift to decrease pressure. So how can we decrease the pressure in that system? Well, no, the volume. So we've decreased the volume. So the volume is now going to be fixed. So we're not going to change the volume. What can we change? We can change moles. Okay. So if we want pressure is directly proportional to the amount of gas, the moles of gas. So if we want to decrease pressure, we need to decrease the moles of gas. So which way will this go? It's going to go to the right. Okay? Because we have 4 moles of gas on the reactant side. We only have 2 moles of gas on the product side. Okay? So the way that we can decrease pressure is decrease N, decrease moles, and that will be, and I'll write it over here, shift right. Okay, going from 4 moles of gas to 2 moles of gas. Yes?
So if there was like a liquid or a solid in the system, would you like not count that?
You would not count liquids or solids. Okay? You know, liquid, technically, I mean, its pressure is not 0. Okay, because there is a vapor pressure of a liquid, but we will assume that the pressure of the liquid is much less than that of the gases. Solids really wouldn't have any pressure, except that if you had so much solid that it was filling up the container. But again, so you're making some assumptions here, but yeah, don't look at liquids or solids when you're doing these. Just look at the gases. Okay, good question. Question?
Work it out.
Oh, just trying to work it out, okay. All right, next one, we're going to raise the temperature. What do we do with that one? You do need to look at delta H, exactly right. So This says that your delta H is negative, which means what? Exothermic. We talked about that on the Friday review session, making sure you know the sign conventions for enthalpy change and delta S and delta G and all that good stuff. All right, so this is exothermic. Reaction releases heat, or we can think of produces heat. So if it's exothermic, heat technically is not a product, but if it's exothermic, we think of heat as a product. The reaction produces, releases heat. So now we're going to raise the temperature. So in effect, we're adding more thermal energy. We're adding more heat. So treating this as any other product, and we are now adding that, adding heat, raising the temperature. Which way will this shift?
Left.
And we'll shift left. So just like any product, if you were to add a product, it's going to shift to remove the product. It's going to shift back to the left. Okay. So I think 3 and 4 on here are the ones that you have to think most about. Changes in the amount of a gas, I think are pretty easy. Be careful. Same thing with kind of going to your question. If we were to add or remove a liquid or a solid, that would have no effect either. We don't have a liquid or solid in this reaction. But if you did, adding or removing a liquid or solid would have no effect. But these two, changing the volume of the container or changing the temperature, there's more to think about. So make sure you can think through those. All right, 5 and 6. Let's do 5 first. If we add an inert gas, does that affect the equilibrium position? No. So this one would be no change or no effect. What about adding a catalyst? No, that has no effect either, no change. Now the catalyst will speed up the reaction. You will get to the equilibrium position faster, but you're still going to get to the same equilibrium position. Okay, because remember, a catalyst doesn't change your reactants and products. You still have the same reactants, you still end up with the same products. So the equilibrium position will be the same. You just get there faster. All right, let's see what else we have here. Know that the equilibrium constant is a constant at a given temperature. So if we do change the temperature, the equilibrium constant will change. Okay? So note that in 4, when we raised the temperature, it shifted left, and so our amount of product would go down, and our amount of reactant would go up. Okay, so our equilibrium constant will certainly change as we change the temperature. Okay? But it is a constant for a given reaction at a given temperature. All right. Any questions about equilibrium in general? That gets most of the kind of the buildup of what is equilibrium, how do you set up the expression, how do you set up an ice table, all the kind of fundamentals that we did then kind of use in the next 2 chapters. Good? All right. Perfect timing. Now we're getting to the material that most of this we did after spring break. Okay, so this should be the material you're still most familiar with. We did a little bit of acid-base before spring break. There was a little bit of acid-base stuff on the second exam, but most of the acid-base and buffers and all this material was after spring break. All right, acid-base definitions, always good to know because they really, you could get a question that's just asking definitions, possibly, but they're also really helpful in writing the correct reaction. If you don't know what a Bronsted acid is, or an Arrhenius acid for that matter, it's harder to write the correct reactions. So what is a Bronsted acid? Hydrogen ion donor. Okay. We also call those proton donors because the main isotope of hydrogen, when it loses its 1 electron, all it has left is a proton. but I like to say hydrogen ion because that's how we're going to represent it in the reaction. Bronsted base. Hydrogen ion acceptor. H plus acceptor. All right, let's do Arrhenius. What do Arrhenius acids produce? Hydronium. Okay, we could say H plus, but we typically say hydronium. Arrhenius acid produces, acids produce hydronium. Okay, and again, that's good to know when we're writing out these reactions. If you know you have an acid, you better get hydronium as a product, particularly for most reactions. When we get to Lewis acids and bases, those can be different. But for the bulk of what you need to know for this final exam, if you have an acid, it better produce hydronium in water. Arrhenius base. They produce hydroxide. All right, got those? Next thing on the list. Know the relationships between hydronium and hydroxide, and also pH and pOH for neutral, acidic, and basic solutions. Okay. So let's start with neutral. And again, we're going to be looking at 25 degrees Celsius. Okay, what can you say about hydronium compared to hydroxide in a neutral solution? They are equal. Now, that's regardless of temperature. Okay, neutral solution, hydronium equals hydroxide. Now, at 25 degrees Celsius, what do they equal? These two concentrations, if it's neutral. Oh, come on. Well, pH is 7, but what is my hydronium and what is my hydroxide concentration? At 25. 1 times 10 to the negative 7th, exactly. Okay. So that's where if you take the negative log of that, that's where you get a pH of 7. Okay? So the reason why we use a negative log scale is these concentrations, well, certainly in water, they're really small. So rather than talk about, oh, my hydronium is 1 times 10 to the negative 7th molar, I can say, oh, my pH is 7. It just kind of simplifies how we express it. Okay, so that's concentration. Why don't we go do concentration first before we get to, well, let's do pH and pOH here. Why not? So for neutral solution at 25 Celsius, pH will equal to pOH, well, just in general. And then at 25 Celsius, they will both equal what? 7. Oh, let me just tack it on here at the end. They'll both be 7. All right, acidic. What can you tell me about the general relationship between hydronium and hydroxide if it's acidic? Okay, more hydronium. Acids produce hydronium, so our hydronium ion is going to go up. Our hydroxide will go down. Okay, so acids have more hydronium. There's still hydroxide in an acidic solution. It's just going to be less than the hydronium. And it could be quite less, but hydronium, there should be a, that's supposed to be an 8. Come on, there we go. Hydronium is greater than hydroxide. pH, less than 7. So acidic pH is less than 7. So if pH is less than 7, POH will be greater than 7. And we'll write down the relations. You probably know them. pH plus POH is equal to 14 at 25 Celsius. And last one, basic. Hydronium compared to hydroxide. Hydroxide's greater or hydronium is less than hydroxide. Okay, again, bases produce hydroxide, so your hydroxide goes up, your hydronium goes down. Okay, they're going to go opposite directions from each other. And then what about pH? For basic, greater than 7. If pH is greater, POH will be less than 7. Okay, so again, hydronium and hydroxide are going to go in opposite directions. pH and POH will go in opposite directions as well. Okay, so that's good to know. Make sure you can calculate hydronium from hydroxide or vice versa. How would we do that? So if I give you if it says this solution has a hydronium concentration of this, what's hydroxide? You don't want to miss that on the final. How would, okay, exactly right. So we know that Kw is equal to hydronium times hydroxide, and at 25 Celsius, Kw is 1 times 10 to the negative 14th. Okay, so we have our constant. If we're given hydronium, we have those two things, we solve for hydroxide. Okay, or I could give you hydroxide, knowing that Kw, solve for hydronium. Okay, so that it's probably going to be on the final. Don't miss something like that. Those are pretty straightforward. Now remember where this equation comes from. That comes from the equilibrium of pure water. So these are all aqueous solutions. So even though we're dissolving acids and bases in water, the equilibrium of water is still always present. There's lots of water there in that solution. So this equilibrium constant expression comes from this equilibrium where one water molecule is acting as an acid, donating an H+. So this water molecule on the left is acting as an acid. The water molecule on the right is acting as a base. It's accepting the H+. And when this water accepts an H+, we produce hydronium ions. And when the first water loses an H+, we get hydroxide ions. Okay? So that's the equilibrium of pure water that's present in any aqueous solution that we're dealing with. Okay? And pure liquids do not enter into the equilibrium constant expression. So these reactants do not enter in. So our equilibrium constant expression is just hydronium times hydroxide. And that's where that expression comes from. We did look at that when we first did acids and bases, but that was before spring break, and you might not remember that. But it's good to know. All right, be able to calculate hydronium from pH or hydroxide concentration from POH. How do we do that? 10 to the negative pH. So just looking at pH, it's just rearranging the equation. We know that pH is the negative log of the hydronium concentration. If we first multiply through by -1, we'd get negative pH is equal to log of hydronium. And then to solve for hydronium, we need to get that log base 10 term out of the front of hydronium. So how do we do that? 10 to the x, 10 raised to the x, so 10 to the negative pH, 10 log of hydronium. This on the right is just going to give us the hydronium concentration. So hydronium is 10 raised to the negative pH power. Okay. We can do the same thing for hydroxide from POH. Okay. Same rearranging the equation, and you would end up with the same similar equation. Hydroxide is 10 raised to the negative POH power. Okay. And then don't forget that pH plus POH is equal to 14. Okay, so we could always convert, if you're given POH, but you want hydronium, you'd probably want to get the pH first before you get the hydronium. Okay? All right, what else? So there's still a lot left in this chapter. Conjugate acid-base pairs. What do they differ by? One hydrogen ion. Okay, so when the acid donates its H+, then you'll have left behind the conjugate base of that acid. Okay, so just a couple of different if we had hydrochloric acid, strong acid, what would its conjugate base be? Cl minus. Okay, differ by one H+. Okay. What if I had something like H2PO4 minus, and this was the acid? What would its conjugate base look like? HPO4 2 minus. Okay, again, it's only differing by a single hydrogen ion, and the acid, and I didn't write acid, but we know this is hydrochloric acid. This is its conjugate base. Okay. So the base has, the acid has one more H+, or you can think of the conjugate base having one less. So if this is our acid, take away one hydrogen. Okay. Now we can also go the other way. If we have a base, we can write its conjugate acid. So here's ammonia, which is a base. What does its conjugate acid look like? NH4+, so one more H+, so this would be the conjugate acid of that base. Okay. Be careful. Some of the bases are hard, the weak bases are hard to recognize. This would be another weak base. What would the conjugate acid of that weak base look like? Okay. Okay, so the acid is going to have one more H+. That H+ is going to be bonded to the nitrogen. Remember, it's a nitrogen that has a lone pair that can accept the H+. And so we write the hydrogen ion next to the nitrogen. Okay, so again, key difference, just a single H+. The acid has one more H+ than the base. Same thing here. The acid, this is the conjugate acid, one more H+ than that weak base. All right, finally some pH calculations. pH of a strong acid or strong base. Easy? Okay, so if you had first off, make sure you know your 6 strong acids and your 6 strong bases. Okay, and I should have put that in the study guide. I don't think I wrote that in there. But you do need to know your 6 strong acids, so let's write those. We know HCl, what else? Okay, HI. Let's throw HBr in the middle of that. So there's 3 or 6. So if you look at the halogens, well, HF is not, so don't start at the top, but HCl, HBr, HI. What else? Okay, sulfuric, H2SO4. You've heard of that one. What else? Nitric acid, HNO3. And one more. Perchloric, HClO4. Those are the 6 common strong acids. Okay? Again, those are important to know because the problem most likely is not going to say calculate the pH of this strong acid. It will just say calculate the pH of HNO3. Okay? Or HI. All right? So something like that. So you need to know it's a strong acid. So if you have a strong acid, what do we assume about that strong acid? It completely ionizes. So that HCl in water completely ionizes 100% to hydronium and the conjugate base. Okay, so again, writing the reactions for this one isn't as important because if you know it ionizes completely, you don't have to do this much work. But what we assume for a strong acid is the equilibrium constant is so large. The equilibrium constant for HCl is about 1 × 10 to the positive 6. Okay, so it's very large, which means we're going to have mostly product. And so it's going to be so far to the right, we're just going to say, let's go all the way to the right. So if all of this reacts, 0.01 molar, how much product do we get? Right, so our hydronium, okay? And if we want to write, you don't have to write all this out, but all of that strong acid is going to ionize, and we are going to produce 0.01 molar hydronium. Okay, so again, if you know how to do a strong acid problem, you just look at the concentration, say, oh, well, that's equal to the hydronium, take the negative log of it, and you are done. So for this one, you should get a pH of 2.00. Okay? About our 6 common, or really not common. There's a couple of hydroxide salts that are kind of marginal as far as strong bases. So sometimes you'll see a list of about 8. Let's just keep it simple and have a list of 6 strong bases as well. And what do those look like? Okay. What else? Okay, so let's just start at the top of the alkali metals. Hydrogen is not an alkali metal, so lithium, sodium, potassium, rubidium, and cesium. So there's 5 of your 6 just going down the alkali metal hydroxides. And then there's 1 alkaline earth metal hydroxide. Yeah, so go across from cesium, barium hydroxide. Okay. Now, strontium hydroxide, so going above barium, strontium hydroxide and calcium hydroxide are slightly soluble. So sometimes you'll see those classified as strong bases as well. You won't see those on the final exam. So know these 6 as well. Okay. So if you have 0.001 molar NaOH. What do you do with that? Okay, so what is my hydroxide concentration? Yeah, it's going to be the same concentration as that sodium hydroxide. Same reason, this is a soluble salt, so we assume it completely dissociates. So sodium hydroxide in water will go 100% to sodium ions and hydroxide ions. So all of that sodium hydroxide dissolves, so the hydroxide concentration will equal to the starting concentration of sodium hydroxide. So hydroxide is 0.001 molar. Wow, that was nice. Surprised it took that long. Gosh. See how much noise I can make here. All right. So hydroxide is 0.001. I heard somebody say take the negative log. That will give us our POH. We'll get a POH of 3. Okay, so the negative log of 0.001 is going to be the POH since that's hydroxide. And then what do we do with that? Subtract it from 14, and you'll find a pH of 11 for that. Okay. Now the one strong base to watch out for is barium hydroxide, because when that dissolves, for every 1 unit of barium hydroxide, you're going to get 2 hydroxides. So your hydroxide is going to be double whatever the concentration of barium hydroxide is. So if my barium hydroxide was 0.001 molar, okay, since I get 2 hydroxides for every one of those, my hydroxide, let me just write it here, for that one, would be double that, so it would be 0.002 molar for that solution. Okay? So almost guaranteed you will see either strong acid or strong base on the final exam. Okay? But since they dissociate completely or ionize completely, the calculation's fairly straightforward. All right. Be able to calculate pH and percent ionization of a weak acid or a weak base. So let's do one of these. Let's do hydrocyanic acid. It's a pretty darn weak acid. It has a Ka of 4.9 times 10 to the negative 10. Okay. So how would you know that's a weak acid? I just told you it was, but I'm not going to tell you on the final. Ka value would certainly give it away. What else? It's not one of the 6 common strong acids. Okay. It starts with hydrogen in the formula. So when you see hydrogen there, that's probably going to say, oh, well, that's probably an acid. The Ka value would definitely confirm that, and it's not one of my 6 strong acids. So we do need to set up an ice table for this one. Now here is where it's important to write the correct reaction in water, and this is where the definitions of a Bronsted acid and base and an Arrhenius acid and base should guide you. Okay? So this is an acid. So what is it going to do in water? Donate a hydrogen ion. And what will it produce? Hydronium. Okay? So when water gains that H+, we produce hydronium ions in solution, and we also get the conjugate base of that acid. So that acid loses an H+, and we're left with its conjugate base. All right, it's 0.01 molar. That's our initial concentration of that acid. Okay. We'll assume that the products are essentially 0 before we start. Which way does this shift to reach equilibrium? It has to go to the right. We're not going to get much product, right? This is a really small Ka. So we're not going to get much product, but we will get a little bit of product. So it has to go to the right. So this has to be minus x, plus x, plus x. Okay, so I think the ICE tables for weak acids and weak bases are pretty straightforward. Okay, so what do we do with those equilibrium values?
Set equal to the Ka.
Set it equal to the Ka. So our Ka value, 4.9 times 10 to the negative 10th. And its products, now in this case, our coefficients are all 1, so it makes it easy. You don't have to worry about raising to the power of the coefficient. So it's just x times x, which is, let's just write that as x squared. So x times x for our products. Over 0.01 minus x. So what do we do here? Yes. Small x approximation. Okay. So it's in the study guide in the previous chapter, but I said let's save this for a weak acid or weak base problem. Really small Ka. Again, typically for your weak acids and weak bases, those values will be 10 to the minus fourth or less. So almost always you can make the small x approximation. So again, that approximation is, we know very little is going to go to product. Okay, so most of this reactant is going to stay as reactant. So we're going to assume that this concentration does not change appreciably. So 0.01 minus x, we're going to assume stays about 0.01. Okay, which makes our calculation definitely easier because we can just get rid of that x. Okay, so multiply 4.9 times 10 to the negative 10th times 0.01 and take the square root. So 4.9. And we should get an x value of 2.21 times 10 to the negative 6th molar. And that x equals what in our reaction? Hydronium. So again, since this is an acid, it produces hydronium. So that x that we solve for, that is our hydronium concentration. So to get the pH, we just take the negative log of that. About 5.65. It's 5.655, but about 5.65. Okay, stop for a second and look at that answer and just say, does it at least make sense? Okay, this is a weak acid, and it's a pretty darn weak acid. You can tell that by the Ka value, but it should still be acidic. And so this solution is slightly acidic, 5.65. Okay, percent ionization. What do we do with that? Divide x by the initial. So x is the amount that reacted. So that's the part that reacted. The whole amount is the initial amount of acid that we started with. Part divided by the whole. That gives us a fraction. Multiply by 100 to get a percentage. So let me just do that down here. So our percent ionization, in this case, the part that reacted is x. The whole amount is what we started with, the initial. Multiply by 100 to get a percentage. And, when you do these calculations for the final, you should keep all the, more sig figs than are given in your answer. This was actually 2.2136. If we actually carried a few extra sig figs in our number here. If you don't do that on the final, the answer you get might be a little bit off from one of the choices on the multiple choice, so it's good to carry some extra sig figs. Initial 0.01, multiply by 100. And I get a percent ionization of 0.022. I think we really only had 2 sig figs to start. 0.022%. Is that what you expect for a weak acid? Yeah, weak acids do not ionize much. They only partially ionize. Now, when we talked about weak acid, we said, well, your typical weak acid ionizes about 1%. Okay, but it varies depending on the acid. This is a really weak acid, 10 to the negative 10th. Most of the weak acids that you're going to see are in the 10 to the negative 5th range. So this is pretty weak, and so this one is not going to ionize very much. Okay, about 0.02%. All right, we've already talked about this next bullet. We did the strong acids. So kind of half the battle on some of these pH calculations is knowing what you have. Okay, you know, if I say calculate the pH of a 0.1 molar solution of HNO3, and you don't know HNO3 is a strong acid, then maybe it's not so easy a calculation. So we went through our strong acids already. We went through our strong bases. We talked about how to identify a weak acid in this problem up here. Look for something that starts with hydrogen. Look for a Ka value. That would be a tip-off. One other thing you should look for weak acids is COOH. And what is that? That is a carboxyl group, and hence an acid that has that as a carboxylic acid. So those are weak acids. So watch for those. And then we really haven't talked about weak bases yet. But weak bases are a type of compound called amines or amines. And what's the key structural feature of an amine? Okay, so I heard somebody say NH3, nitrogen. So all the amines will have a nitrogen with 3 bonds. Okay, doesn't necessarily need to be 3 single bonds. It could be a double and a single, but it will have 3 bonds. But because it only has 3 bonds, to complete the octet, the nitrogen will have a lone pair. Okay, and it's that lone pair that can be, that we can either think of it as accepting the H plus as a Bronsted acid, or donating that electron pair, which is a Lewis base, which we'll talk a little bit about in a minute. Okay, but that's the key feature of weak bases. Now, the simplest one that you're familiar with is ammonia, where the 3 things that are bonded here are all hydrogens. Okay, but they don't have to be hydrogens. They can be methyl groups or ethyl groups, or we can even have a ring structure or things like that. But three bonds with a lone pair on nitrogen. Those are our weak bases. Okay with that? So again, when you're given a pH calculation, take a second and say, oh, what do I have in solution? Is it a strong acid? Is it a weak acid? Is it a strong base? Is it a weak base? Okay, and then they'll probably help you get to the right place for the calculation. I think this one's pretty straightforward. Understand the difference between the percent ionization of a strong acid compared to a weak acid. Pretty straightforward. What do we assume about percent ionization for a strong acid? 100%. Weak acid? Yeah, it's typically very small. Okay, typically on the 1% side. Okay, one thing that I did not point out, so let's scroll back up here very quickly. This percent ionization, one of the bullet points in the equilibrium chapter said know what the 5% rule is. And what is the 5% rule? What's that?
If the percent ionization is below 5%,
then well, yeah, but what else does that allow us to do? Small x approximation. But you're right, yeah, weak acids are typically going to be less than 5%. The one thing you have to be cautious with, and we really didn't spend any time on it, as you dilute the weak acid, if it gets very, very dilute, its percent ionization goes up. And so a weak acid can ionize significantly more if it's a really, really dilute solution. But the typical concentrations we're looking at, weak acids typically only ionize, around 1%, a couple of percent in that ballpark. But this is also our test for, is our small x approximation valid? And that needs to be less than 5%. X needs to be less than 5% of what we start with. And this one is certainly valid. X was only 0.02% of what we start with. So that's the 5% rule, just checking whether your approximation's valid. Next bullet point here, calculate Ka for a conjugate acid from the Kb value of its base or vice versa. How do we do that? Okay, so Kw is Ka times Kb. Okay, so if we wanted to solve for Ka, okay, so where you're going to see that most likely is probably for a salt solution or maybe for a buffer. You might have to calculate the Ka from the Kb or the Kb from the Ka. Okay, so make sure you can do that. That equation's on the equation sheet, so you don't have to memorize it, but you need to know how to use it. Next one. In addition to doing the calculation, you should know qualitatively the relationship between the strength of an acid and the strength of its conjugate base. So fill in the blank. The stronger the acid, the weaker the conjugate base. Okay, so they go in opposite directions. Okay, and this becomes important when we're looking at salt solutions. And is, for example, is the conjugate base of this acid a base or not? Okay, we can restate this another way. We could then go the weaker the acid, or then the conjugate base will be stronger. The weaker the acid, the stronger the conjugate base. Okay, so a couple of things there. We have HNO3 with its conjugate base NO3 minus, and HNO2 with its conjugate base NO2 minus. Which of those bases is stronger? So NO3 minus or NO2 minus? Which would be the stronger base? NO2 minus. Okay, so HNO3 is a strong acid, versus HNO2 is a weak acid. So you can see why it's good to know your 6 strong acids. So HNO3 is one of those. HNO2 is not, so that is a weak acid. And so if it's a conjugate base of a strong acid, that's an incredibly weak base. Okay? Negligibly, I can never spell this word. I think that's right. Okay, so strong acid, the conjugate base is going to be so weak. Okay, it's not going to produce hydroxide. But the conjugate base of a weak acid this will be a weak base and it will produce hydroxide in water. Okay, so it's important to be able to distinguish those. Okay, along those same lines, it really ties into what we just talked about. If I gave you two salt solutions, and just asked, take a look at NaNO3 as that solution, as a solution of that salt, so that salt dissolved in water, so an aqueous solution of this, so I should write AQ after this. Is it acidic, basic, or neutral? So NaNO3, it's going to be neutral. Okay, so remember, alkali metal cations aren't going to do anything. So this salt is Na plus and NO3 minus. Those are going to dissociate in water, so those are separate from each other. Okay. There are certain metal cations that are acids, but not the alkali metal cations and the alkaline earth metal cations. So sodium's not going to do anything. And we talked about, well, the conjugate base of a strong acid really has no base strength in water. So this will not change the pH, and this one will be neutral. Sodium nitrite, on the other hand, NO2 minus is the conjugate base of a weak acid. So we just talked about that is a weak base. So that salt will dissolve in water will produce what? A basic solution. Okay. Watch for salt solutions like that as well. NH4, so something with a cation that's not a metal. Okay. So what about that salt? This one will be acidic. So chloride is the conjugate base of a strong acid. Okay, and again, the stronger the acid, the weaker the conjugate base. So chloride is not going to do anything in water, conjugate base of a strong acid. But what do you know about ammonium? Conjugate acid of a weak base, ammonia. Remember, the acid has one more H plus in the base. So take away an H plus from ammonium to get, well, that was supposed to say ammonia, NH3, which is a weak base. So if ammonia is a weak base, then ammonium, NH4 plus, is what? That is a weak acid. So that solution will be acidic. Okay? So that's the qualitative piece. And then the last thing I have, I'll have to look at the final. I haven't really looked at it closely for a few days. I don't have anything on here about Lewis acids and bases or acid strength based on structure, so I will double check those before the next session tomorrow. But the last thing on here for this chapter is actually calculating the pH of a salt solution. Okay, so let's, since we've been talking about NaNO2 a little bit, let's stick with that salt solution. So if I want to calculate the pH of that salt solution, what do you need to do? We've already done some of the work already, right? One, you got to identify what's an acid or what's a base. Have we done that? Yeah. So what's going to affect the pH of the solution? NO2 minus. So it scrolled off the screen, but look back in your notes. We determined that NO2 minus as the conjugate base of a weak acid was a weak base. Okay, so you have to do that part first. So once we figure that out, NO2 minus is a weak base, conjugate base of a weak acid. Again, these are all aqueous, so we do need to write out the correct reaction. So that weak base is going to do what? Accept a hydrogen ion. Bronsted base, hydrogen ion acceptor. Accept an H+. When it accepts the H+, we get its conjugate acid. That should not surprise you. But more importantly, what else do we get? What's our other product? Hydroxide. Bases produce hydroxide. That's the Arrhenius base definition. Okay? So salt solutions are not easy. You have to look at the salt. You have to figure out what you have. Okay, we have sodium ion. I know that's not going to do anything. We have nitrite ion, NO2 minus. Oh yeah, that's the conjugate base of a weak acid. Oh yeah, that's a weak base. Now we have to write the reaction of that weak base producing hydroxide. It was 0.1 molar NaNO2, so we have 0.1 molar nitrite. Before that ionizes, the products are 0, or essentially 0. Clearly not at equilibrium. We're not going to get very much product here, but we will get a little bit of product, so it has to go to the right. Nice that all the coefficients are 1. And you've seen this ice table before. No surprise. Now, the ice table itself isn't hard, but you have to have the right reaction. Okay, so use the Bronsted definitions, use the Arrhenius definitions to guide you to write the correct thing. Yes, I'm sorry.
How would we know that the sodium doesn't combine to make NaOH?
Okay, so there are some metal cations that are acids. Okay, there are some that are acids. They would not be bases. So there is no, remember, this is just a solution of water. So you're dissolving salt in water. So there's not going to be very much hydroxide ion in solution from the water anyway. But some metal cations can be acids, things like aluminum 3+, iron 3+, but they tend to have to be small, highly charged cations. So the alkali metal cations aren't going to do anything. They're just going to be spectator ions. So just ignore those. Okay? And remember, we write the salt, oh, that's good. We write the salt like this, but remember, soluble salts completely dissociate. Okay? 100%. So it's not NaNO2, it's actually Na plus in solution and NO2 minus in solution. Okay, so that's what it exists as. So the Na plus doesn't do anything. It's just in solution. It's moving throughout the solution. It's just not reacting. The only thing reacting a little bit is the nitrite, NO2 minus. All right. So this is a base. So what do you need for that base? We need its Kb value. Now, most likely, in a problem like this, you will be given the Ka value for HNO2, which is about 4.5 times 10 to the negative 4th. Okay, so this certainly is not HNO2. It is the conjugate base of HNO2, so we need its Kb value for that conjugate base. So how do we get that? Okay, Kw divided by Ka. So 1 times 10 to the negative 14th, divided by 4.5 times 10 to the negative 4th. And we are going to get about 2.22, let's carry an extra sig fig here, times 10 to the negative 11th. And as you can see, that's a pretty darn weak base. Nitrite is not a strong base. It's very weak, but it is strong enough to produce some hydroxide. Yes.
So is that Kb value designated to the HNO2 or the NO2 minus?
The Kb is for NO2 minus.
Okay, cool.
HNO2 has a Ka value because HNO2 is an acid. Okay, but quite often it's easier to find. Although nowadays, in the old days when you had to look things up in a book, it would have been easier to find the Ka value for HNO2 rather than the Kb value for NO2 minus. And so that's why we still, with a lot of these problems, we still will put in the Ka value for HNO2 just so you know how to do that conversion. So we get the Kb, products x times x squared over 0.1. Is everybody okay with that? Just calling the denominator 0.1 and not 0.1 minus x. Is that okay to do? Yeah, in this case, this is a really small k value, 10 to the negative 11th. We can make the small x approximation. Cross multiply there, take the square root, and you should get an x value of 1.49 times 10 to the negative 6th molar. And what does that equal to? That is hydroxide. So again, nitrite is a weak base. It produces hydroxide. And this is why it's important that you get the correct reaction. Bases produce hydroxide. So this is our hydroxide concentration. So what should we do first? Negative log, which gives us what? 5.83. And that equals what? What is that we just solved for? So we took the negative log of the hydroxide. So that is our POH, 5.83. So our pH is 8.17. Okay. So again, when you get done with the calculation, if you can, it's a good idea just to say, does it at least make sense? Okay. So we determined that nitrite was a weak base. It's actually quite a weak base because that's a very small Kb value, 10 to the negative 11th, but we should still get a basic solution, and it is slightly basic at pH 8.17. Whew. All right. Is that enough for tonight? No? Well, so let's look at what we have for tomorrow night. We really have, so I went through 2 chapters on Friday. We did 2 chapters tonight. We essentially have 2 full chapters left. Buffers, titration, solubility, and the electrochem. There is very little from nuclear. It's just balancing equations and then really first order kinetics, which you already know. So we essentially have 2 chapters left to go through the most recent material, so that should be what you're most familiar with. So we will meet again tomorrow night at 5 o'clock, same room. Okay, and that should get us through the review. Again, section 2, you guys are taking the final Tuesday at 12:30. If you're in section 3, you still have more time. We will be taking the final on Thursday. Okay? Don't forget that Alex closes tonight. It's your last chance. Alex closes at midnight tonight. If you have any questions, come on down. Don't forget about the practice finals that are in Blackboard. So what happened to a lot of students? Let me close this down here.